Welcome to our journey through the layers of Earth's atmosphere. Our atmosphere, a delicate veil held by gravity, is a wonder of nature. It's a giant, invisible ocean, a sea of air that surrounds our planet, protecting and nurturing life. Each layer, from the ground up to the edge of space, plays a vital role in supporting life and enabling various atmospheric processes. Think of it like a multi-layered cake, each layer with its own unique ingredients and properties. We'll peel back these layers one by one, exploring the characteristics that make each one special. From the air we breathe to the ozone layer that shields us from harmful radiation, we'll uncover the secrets hidden within our planet's life support system. So fasten your seatbelts and get ready for an incredible voyage through the very air we breathe. Let's begin our ascent into the magnificent tapestry of Earth's atmosphere. We begin our journey right here where we live and breathe, the troposphere. This layer, extending from the surface up to about 7 to 15 kilometers, is the densest layer of our atmosphere, containing most of its mass and virtually all of its water vapor. That's why this layer is the theater for our weather. The troposphere is a turbulent realm. Warm air, heated by the Earth's surface, rises and collides with cooler air above, creating the winds, clouds, rain and snow that define our weather patterns. It's a dynamic system, constantly in motion, shaping the landscapes and climates we experience on Earth. Think of the troposphere as a giant heat engine. Sunlight warms the Earth's surface and the air above it heats up, becoming less dense and rising. This rising air creates areas of low pressure, drawing in cooler, denser air from surrounding areas, and thus the winds blow. As we ascend through the troposphere, we notice a distinct drop in temperature. This temperature gradient, known as the lapse rate, is responsible for the formation of clouds. Warm, moist air rises, cools, and the water vapor condenses around tiny particles in the air, forming the familiar shapes of clouds. The troposphere, though just a thin layer compared to the vastness of space, is the stage for the drama of weather, a constant reminder of the powerful forces at play in our atmosphere. As we leave the troposphere and enter the stratosphere, we are reminded of the interconnectedness of these layers. The tropopause, the boundary between the two, acts like a lid, preventing most of the water vapor from escaping into the layers above. This is just one example of how each layer of the atmosphere, though distinct in its properties, interacts with the others to create the complex and dynamic system that sustains life on Earth. Leaving the turbulent troposphere behind, we ascend into a region of relative calm, the stratosphere. Here the air thins and the temperature, surprisingly, begins to rise with altitude. This temperature inversion is due to the presence of a very special molecule, ozone. Ozone, a molecule made up of 3 oxygen atoms, is the star of the stratosphere. It absorbs most of the sun's harmful ultraviolet radiation, shielding life on Earth from its damaging effects. This protective layer, known as the ozone layer, is crucial for life as we know it. Imagine the sun as a giant furnace, emitting not only light and heat, but also invisible rays of ultraviolet radiation. These ultraviolet rays, if they reached Earth's surface unchecked, would be harmful to life, causing skin cancer, cataracts, and damage to plants and animals. The ozone layer acts like a giant sunscreen, absorbing most of this harmful radiation and preventing it from reaching the ground. It's a silent guardian, protecting us from the sun's invisible fury. The stratosphere is also a domain of remarkable stability. Unlike the troposphere with its turbulent weather patterns, the stratosphere is relatively calm. The air here is dry and less dense, with little vertical mixing. This stability makes the stratosphere a haven for certain types of aircraft. Jet planes often cruise in the lower stratosphere, taking advantage of the smooth, less turbulent air to conserve fuel and provide a more comfortable ride for passengers. As we ascend higher into the stratosphere, the air becomes increasingly thin and the temperature gradually decreases until we reach the stratopause, the boundary between the stratosphere and the next layer, the mesosphere. The stratosphere, with its protective ozone layer and stable conditions, reminds us that Earth's atmosphere is not just a random mix of gases, but a finely tuned system shaped by both physics and chemistry to support life. Our journey through the atmosphere now takes us to the mesosphere, a realm of extreme cold and thin air. This layer, extending from about 50 to 85 kilometers above Earth, is where most meteors burn up upon entering our atmosphere. Imagine yourself standing on Earth gazing up at the night sky. You might be lucky enough to see a shooting star, a streak of light flashing across the darkness. What you're witnessing is a meteor, a small piece of space debris burning up in the mesosphere. These meteors, traveling at incredible speeds, collide with air molecules in the mesosphere, generating intense heat from friction. This heat vaporizes most meteors, creating the fiery streaks we see as shooting stars. The mesosphere, though less dense than the layers below, plays a crucial role in protecting us from these celestial intruders. It acts as a shield, intercepting countless meteors every day and preventing them from reaching Earth's surface. The temperature in the mesosphere decreases with altitude, reaching its coldest point at the mesopause, the boundary between the mesosphere and the next layer, the thermosphere. Here, temperatures can plummet to -90 degrees Celsius or even lower. This extreme cold is a result of the thin air and the decreasing absorption of solar radiation. With fewer air molecules to absorb and retain heat, the mesosphere becomes a frigid realm. Despite its extreme conditions, the mesosphere plays a vital role in protecting us from meteoroids and shaping the dynamics of our atmosphere. We now ascend into the thermosphere, a layer that stretches from about 85 to 1,000 kilometers above Earth. Here, the air is incredibly thin, and temperatures soar to extreme highs due to the absorption of high-energy solar radiation. Imagine a world where the air is so thin that molecules rarely collide, where the concept of temperature takes on a different meaning. This is the thermosphere, a layer where the laws of physics seem to bend. Unlike the layers below, where temperature is determined by the collision of air molecules, temperature in the thermosphere is a measure of the energy of individual molecules. These molecules, energized by solar radiation, vibrate and move at incredible speeds, giving the thermosphere its extraordinary temperatures. But don't let the high temperatures fool you. The air here is so thin that it wouldn't feel hot to us. In fact, if you were exposed to the thermosphere without a spacesuit, you would feel incredibly cold due to the lack of air molecules to transfer heat. The thermosphere is also home to the ionosphere, a region where solar radiation ionizes atmospheric gases, creating a layer of electrically charged particles. This layer plays a crucial role in radio communications, reflecting radio waves back to Earth and enabling long-distance communication. Imagine sending a radio signal from one side of the world to the other. Without the ionosphere, these signals would simply travel out into space, never reaching their destination. The ionosphere acts like a giant mirror, reflecting these signals back down to Earth, allowing us to communicate over vast distances. This layer is also where the aurora borealis and aurora australis, the mesmerizing northern and southern lights, occur. These spectacular displays of light are created when charged particles from the sun interact with gases in the thermosphere, exciting them and causing them to emit light. Our journey through Earth's atmosphere culminates in the exosphere, the outermost layer, where the atmosphere gradually fades into the vacuum of space. This layer, extending from about 1,000 kilometers to as far as 10,000 kilometers above Earth, is a realm of extreme thinness where molecules are so sparse that they rarely collide. Imagine a world where the air is so thin that atoms and molecules can travel for kilometers without bumping into each other. This is the exosphere, the final frontier of Earth's atmosphere, where our planet's gaseous envelope merges with the vast emptiness of space. Here the pull of Earth's gravity weakens and some molecules, particularly lighter ones like hydrogen and helium, escape into space, forming a tenuous atmospheric halo around our planet. This escape of atmospheric gases into space is a slow but continuous process. The exosphere is also home to many satellites orbiting Earth at altitudes where atmospheric drag is minimal. These satellites, instruments of our technological ingenuity, provide us with invaluable data about our planet, enabling us to study weather patterns, monitor climate change, and communicate across vast distances. Imagine looking down at Earth from a satellite in the exosphere. You would see our planet as a vibrant blue and green sphere, surrounded by the blackness of space, a sight that underscores both the beauty and fragility of our home in the cosmos. The exosphere, though incredibly thin, is not entirely empty. It's a region of subtle interactions where the solar wind, a stream of charged particles from the sun, interacts with Earth's magnetic field, creating a region known as the magnetosphere. This magnetosphere, a protective bubble surrounding our planet, shields us from the full brunt of the solar wind, deflecting most of its harmful radiation and charged particles away from Earth. Without the magnetosphere, life on Earth would be exposed to the sun's fury, making our planet a much less hospitable place. Thank you for joining us on this exploration of Earth's atmosphere. From the turbulent troposphere where weather shapes our daily lives, to the exosphere's ethereal boundary with space, each layer is essential in its own way, making our planet a unique and habitable place. Our atmosphere, a delicate balance of gases, temperature and pressure, is a testament to the intricate workings of nature. It's a reminder that we are part of a much larger system, interconnected with the cosmos in ways we're only beginning to understand. As we continue to explore our planet and the universe beyond, let us remember the importance of protecting this thin blue line that makes life on Earth possible.